What if you could look back in time, not just centuries or millennia, but all the way to the very first moments of our universe? What would you see? Close your eyes and picture this: a trillionth of a second after the Big Bang. That number is almost impossible to grasp. It's so brief, so instantaneous, that even light barely had time to cross a single atomic nucleus. Yet in that unimaginably small sliver of time, everything we know, the stars above us, the planets, the very atoms in our bodies, was being forged in a firestorm of creation. This is where our story begins, a story written not in years or centuries, but in moments that flickered in and out of existence faster than thought itself. This journey takes us to a place where the laws of physics as we understand them were still taking shape. There was no space as we know it, no time ticking steadily forward, only a seething, energetic chaos, hotter and denser than anything we can recreate even in our most powerful laboratories. In that primordial inferno, energy and matter were one, swirling in a cosmic dance that would eventually give rise to galaxies, gravity, and life itself. It's a chapter of the universe's history that feels almost like mythology, yet it's grounded in the most advanced science humanity has ever pursued. We're going to explore that breathtaking moment together, tracing the threads that connect that explosive beginning to the world we live in today. You'll discover how the tiniest fluctuations in energy laid the groundwork for the largest structures in the cosmos, and how the birth of fundamental forces set the stage for everything that followed. This isn't just a story about the past, it's a story about us, about how we came to be, and how the universe woke up to its own astonishing potential. So settle in, open your mind, and let's step back into the dawn of everything. But to truly appreciate the significance of that first trillionth of a second, we need to rewind the cosmic clock even further, to the very limits of time itself. This brings us to the Planck Epoch, a period so brief it defies all human intuition. We're talking about the interval from time 0 to 10 to the negative 43 seconds. To even begin to comprehend such a minuscule duration, consider this. A trillionth of a second is to 1 second what 1 second is to 32,000 years. Now try to imagine a slice of time over a trillion times shorter than that. This is the Planck scale, a realm where the universe was not just young, but was smaller than a single subatomic particle, a singular point of unimaginable density and heat where the very concepts of space and time as we know them cease to have any clear meaning. In this primordial state, the four fundamental forces that govern our reality, gravity, electromagnetism, and the strong and weak nuclear forces, were not separate entities. They were fused into a single, unified superforce. Everything was one. The universe operated under a set of laws we can only dream of understanding, a perfect symmetry where the rules for the very large and the very small were identical. Gravity, which now dictates the orbits of planets and the pull of a black hole, was inextricably linked with the forces that hold atoms together. It was a time of ultimate unity, but also of incredible turbulence, where the fabric of spacetime itself was believed to be a chaotic foam, bubbling with quantum fluctuations. Particles and energy would spontaneously pop into and out of existence, a seething, energetic chaos that was the true starting point of everything. This era represents the final frontier of human knowledge and the ultimate challenge for modern physics. Our two most powerful theories, Einstein's general relativity, which beautifully describes the force of gravity and the large-scale structure of the cosmos, and quantum mechanics, which with incredible precision explains the behavior of the subatomic world, completely break down under these extreme conditions. They give us contradictory, nonsensical answers when we try to apply them to the Planck Epoch. It's like trying to use a roadmap to navigate the ocean. Our tools are simply not built for this environment. Understanding this period requires a theory of quantum gravity, a way to blend these two monumental ideas into one coherent framework, a goal that has eluded scientists for decades, though candidates like string theory and loop quantum gravity offer promising, if unproven, paths forward. So why does this mysterious, inaccessible epoch matter to our story? Because it sets the initial conditions for everything that follows. The quantum fluctuations that roiled this superforce-dominated universe, these tiny, random ripples in the fabric of reality, were the original seeds. They were the primordial imperfections that, once stretched to cosmic proportions by the inflation to come, would become the gravitational seeds for galaxies, galaxy clusters, and the vast cosmic web we observe today. The universe's entire future structure was written in this first fleeting moment. To grasp the universe at a trillionth of a second is to see the aftermath of this incredible beginning. The first moments after the curtain rose on a drama that is still unfolding 14 billion years later. Now, as we cross that monumental threshold into the first trillionth of a second, the universe undergoes a transformation so profound it defines the very fabric of our reality. Imagine the entire cosmos having expanded from that initial state of perfect unity, finally cooling to a temperature of around 10 to the 15 Kelvin. That's a quadrillion degrees. At these staggering energy levels, something extraordinary happens. The electroweak force, which until this moment had been a single, unified interaction, suddenly splits in two. It's like a single, powerful river forking into two distinct, mighty streams. One branch becomes the electromagnetic force, the familiar phenomenon responsible for light, electricity, and holding our atoms together. The other becomes the weak nuclear force, which governs certain types of radioactive decay and plays a vital role in how the sun shines. This separation isn't a quiet, gentle process. It's a violent, dramatic phase transition, releasing an immense amount of latent energy into the seething cosmos. You can think of it like water freezing into ice. When liquid water freezes, it releases energy and its properties change completely. It becomes a solid, forming a crystalline structure. In a similar cosmic fashion, as the universe cooled through this critical energy threshold, the Higgs field, which had been in a symmetric, high-energy state, suddenly shifted into a broken symmetry state. This change in the fundamental field throughout space is what triggered the force to split and, crucially, is what gave mass to elementary particles. This event, known as electroweak symmetry breaking, is the reason particles like electrons and quarks have any substance at all, allowing them to eventually clump together and form everything we see. This era is so significant because it marks the farthest back in time we can currently probe with any real confidence using our established laws of physics. The Planck Epoch remains a beautiful, tantalizing mystery, but the laws that govern it are still beyond our grasp. Here, at 1 trillionth of a second, the energy scales around 100 giga-electron volts are energies we can actually recreate and study within the giant particle colliders like the Large Hadron Collider at CERN. We are no longer purely speculating about the dawn of time. We are testing these theories by replicating, in a tiny, controlled way, the conditions of the infant universe. We are observing the behavior of matter and forces at these incredible energies, watching as particles zing around at nearly the speed of light in a dense, roaring plasma, providing us with a tangible, experimental window into our cosmic origins. Step into this chaotic, brand-new universe, and you would find yourself immersed in a seething, opaque ocean of pure energy. It was not empty space dotted with objects, but rather a thick, blazingly hot plasma so dense that light itself could not travel freely. Photons, the particles of light, were constantly being absorbed and re-emitted, trapped in a relentless tug of war with other particles. This was the primordial soup, the ultimate cosmic broth, and its ingredients were the most fundamental building blocks of reality. Quarks, the tiny constituents that would later make up protons and neutrons, zipped through this inferno. Alongside them were leptons, a family that includes the familiar electron, and a host of force carriers, gluons, that mediate the strong force, photons for electromagnetism, and the W and Z bosons responsible for the weak nuclear force. In this unimaginably dense environment, the concepts of individual particles as stable, distinct entities almost break down. Matter and energy were constantly interchanging, following Einstein's famous equation. Pairs of particles and their antimatter counterparts, like a quark and an antiquark, would spontaneously burst into existence from the immense energy available, only to meet again a fraction of a moment later and annihilate each other back into pure energy. This frenzied dance of creation and destruction was the dominant rhythm of the cosmos. It was a state of perfect, chaotic balance, but a balance that was destined to be broken. For some reason that remains one of physics' greatest mysteries, this symmetry was not quite perfect. For every billion annihilations between matter and antimatter, a single matter particle survived. This tiny 1 in a billion asymmetry is the reason anything exists at all today. It is the reason we have a universe filled with galaxies and stars, rather than a vast, empty sea of fading radiation. This particle zoo, with all its frenetic activity, was the raw material for everything to come. There were no atoms yet, no molecules, and certainly no planets or people. The universe was far too hot and energetic for quarks to combine into the more complex particles we recognize. They existed in a state known as a Quark-Gluon Plasma, where they flowed freely without being confined. It's a state of matter that we can now recreate for fleeting instants in massive particle colliders, giving us a direct glimpse into the conditions of the universe at this astonishingly early age. This primordial soup, for all its chaos, was not a random mess. The quantum fluctuations from the earlier Planck Epoch and the period of inflation were imprinted onto it, creating tiny variations in density. These minuscule ripples in the cosmic broth were the blueprints, the gravitational seeds from which all future structure would eventually grow. The fate of the entire observable universe was being written in the simmering, energetic interactions of this first trillionth of a second. Even as the universe barreled past that first trillionth of a second, it was still ringing with the echoes of an event that had concluded an almost unimaginable time earlier. This event was cosmic inflation, a period of stupendously rapid expansion that is thought to have ended around 10 to the negative 32 seconds. To put that into perspective, inflation was over and done with by the time the universe was 100 million times younger than it was at our current focal point. Yet its legacy was absolutely everywhere, imprinted onto the fabric of the cosmos in a way that would determine its entire future. You can think of it like a bell that had been struck a single, powerful blow. The initial strike, the inflation itself, was incredibly brief, but the sound waves it produced continued to reverberate, shaping everything that came after. The most crucial gift from this inflationary period was the introduction of minuscule quantum fluctuations. In the seething quantum foam of the very earliest universe, pairs of particles and their antiparticles would spontaneously flicker into and out of existence. This is a normal feature of the quantum world, even in what we perceive as a vacuum. During inflation, however, these tiny, random fluctuations in energy density were suddenly stretched to an astronomical scale. The universe was expanding faster than the speed of light, and it took these microscopic ripples and blew them up to sizes larger than the entire observable universe at the time. What were once quantum jitters became macroscopic variations in the density of the primordial plasma. These ripples were the universe's first and most important structures, even though they were incredibly faint variations of only about 1 part in 100,000. Without these tiny imperfections, the universe would have been a tragic story of perfect simplicity. A perfectly smooth, homogeneous cosmos would have remained just that, a featureless, ultra-hot soup of particles expanding and cooling forever, with no interesting features whatsoever. There would be no clumps of matter, no gravitational seeds to pull matter together. No stars would ever ignite, no planets would ever form, and life would never have had a chance to emerge. The universe would be barren, empty, and utterly boring. The fact that we exist to ponder it is direct proof that the early universe was not perfectly smooth. Those tiny density variations, born from quantum uncertainty and amplified by inflation, were the necessary blueprints for all complexity. They were the gravitational anchors around which matter would eventually gather. By the time we reach 1/trillionth of a second, these imprinted fluctuations are frozen into the fabric of the universe. The plasma, while still incredibly hot and dense, now carries these subtle fingerprints of its inflationary past. Regions that are ever so slightly denser have a slightly stronger gravitational pull. Over the coming hundreds of millions of years, that extra gravity will slowly but relentlessly attract more and more matter from the surrounding areas. These over-dense spots will eventually become the sites of the first galaxies and the immense clusters of galaxies we see today. The entire cosmic web, the vast, intricate structure of filaments and voids that defines the large-scale universe, traces its lineage directly back to these quantum seeds stretched across the sky during that fleeting moment of inflation. This profound connection between the smallest quantum world and the largest cosmic structures is one of the most breathtaking ideas in all of science. While the electromagnetic and weak forces were undergoing their dramatic divorce, another fundamental player was solidifying its own unique identity. The strong nuclear force, which is responsible for holding atomic nuclei together, had by now fully separated and was beginning to assert its immense power over the universe. This force is unbelievably potent. It's the strongest of the 4 fundamental forces, but with an extremely short range, which is why we don't feel its effects in our everyday lives. Its job is to bind quarks together into protons and neutrons, and then to bind those protons and neutrons into the nuclei of atoms. Without it, matter as we know it would simply fly apart. There would be no stability, no structure, no complexity. At this specific moment, however, the universe was still far too energetic for the strong force to do its job in the way we're familiar with. The temperature was an incredible 10 trillion degrees, and under these extreme conditions, quarks and gluons, the particles that carry the strong force, could not stick together. Instead of being neatly packaged inside protons and neutrons, they existed in an exotic, primordial state known as Quark-Gluon Plasma. Imagine a superheated, incredibly dense soup where quarks and gluons zip around freely, unburdened by the confines of larger particles. This was not a gas, not a liquid, not a solid, but a fourth state of matter that behaves according to its own unique rules. A perfect liquid with almost zero viscosity, flowing and swirling without any internal friction. This quark-gluon plasma is a glimpse into a reality that is utterly alien to our own. In today's cold, expanded universe, we never see free quarks. They are permanently confined within particles due to a fascinating property called color confinement. The strong force between quarks actually increases with distance, like a stretchy rubber band. If you try to pull 2 quarks apart, the energy you put into separating them eventually becomes so great that it spontaneously creates a new quark-antiquark pair, resulting in two new bound particles instead of free ones. This is why we can't isolate a single quark. The universe simply doesn't allow it. But back at 1/trillionth of a second, the incredible heat and density provided so much energy that this confinement was temporarily overcome. Quarks and gluons achieved a kind of freedom they would never experience again. The incredible thing is that we aren't just theorizing about this state. Scientists can actually recreate tiny droplets of this primordial Quark-Gluon Plasma here on Earth, inside massive particle accelerators like the Large Hadron Collider at CERN. We slam heavy ions together at nearly the speed of light. For a fleeting instant, in the heart of these microscopic collisions, the energy density becomes so enormous that it melts the protons and neutrons, liberating their constituent quarks and gluons and recreating a speck of the universe as it was at this very moment. By studying the aftermath of these collisions, we can probe the properties of this exotic plasma. We've learned it's not a gas as once thought, but a perfect liquid that flows with minimal resistance, a discovery that has deepened our understanding of how the strong force operates under the most extreme conditions imaginable. These experiments are a form of experimental archaeology, allowing us to test our theories about the universe's first moments by literally recreating them. Amidst the roaring chaos of the Quark-Gluon Plasma, a silent, universe-altering transition was taking place, one that would ultimately make our material world possible. This pivotal moment is known as Electroweak symmetry breaking, and it revolves around a concept that permeates all of space, the Higgs field. Up until this point, the universe was a place of perfect but ultimately barren symmetry. The electromagnetic force and the weak nuclear force were unified as a single electroweak force, and crucially, all fundamental particles were massless. They raced through the primordial soup at the speed of light, unable to form any lasting connections, unable to clump together, and utterly incapable of building the stable structures that would one day become planets and people. The hero of this story is the Higgs field. Imagine it not as a thing, but as a fundamental property of space itself, an invisible molasses-like medium that fills the entire cosmos. For the briefest instant after the Big Bang, this field was in a state of high-energy symmetry, its value resting at zero. In this state, it interacted with particles in a perfectly symmetric way, and everything remained massless. But as the universe expanded and cooled past a critical temperature around 159 giga-electronvolts, the Higgs field underwent a profound phase transition. It shifted from a symmetric state to a broken one, settling into a stable, non-zero value everywhere. This event is what we call the Braut-Inglat-Higgs mechanism, or more commonly, the Higgs mechanism. The consequences of this shift were nothing short of revolutionary. As the Higgs field settled into its new state, it began to interact with various fundamental particles in different ways. Some particles, like the photon, the carrier of light, slipped through this cosmic molasses completely unaffected, remaining massless and forever traveling at light speed. But others, like quarks and electrons, began to drag. They interacted strongly with the Higgs field, and this interaction is what endowed them with mass. It wasn't that the field stuck mass onto them. Rather, their resistance to acceleration, their inertia, came from their continual interaction with this all-pervading field. The more a particle interacts with the Higgs field, the more mass it has. This is why an electron has less mass than a quark, and why a top quark is so immensely heavy. This breaking of symmetry was the single most important event for determining the future character of our universe. Without mass, there would be no atoms. Electrons zipping around at light speed could never be captured by the electrical attraction of a proton to form a stable atom. Without atoms, there would be no molecules, no chemistry, no solids, no liquids, no gases. The universe would be a forever expanding, ultra-hot soup of massless particles and radiation, a featureless and lifeless void. The Higgs mechanism provided the necessary friction to slow particles down, to allow them to attract one another through gravity, to form the first composite structures, and to ultimately build the complex cosmic architecture we see today. It was the moment the universe gained substance and texture, trading perfect symmetry for the rich, complex, and ultimately habitable reality we call home. Yet in this furious, balanced dance of creation and destruction, a mystery was unfolding, one that holds the ultimate answer to why you and I are here to talk about it. According to everything we know about particle physics, the Big Bang should have created matter and antimatter in perfectly equal amounts. For every quark born from the immense energy, an antiquark should have been its perfect mirror. And in the ensuing chaos, they should have completely annihilated each other, leaving behind a universe containing nothing but a fading bath of radiation, expanding into eternal darkness. The fact that we have a universe filled with galaxies, stars, planets, and people is undeniable proof that this perfect symmetry was broken. Somehow, by the time the universe was a mere trillionth of a second old, a tiny, almost imperceptible bias had crept into the cosmic ledger. For every billion pairs of matter and antimatter particles that met and vanished in a flash of energy, a single, solitary matter particle was left behind. 1 in a billion. It seems like a trivial amount, but that 1 in a billion surplus is the reason for everything. All the atoms in your body, all the light from distant stars, every single thing we can see and touch in the entire observable universe is built from the leftover crumbs of that near-total annihilation. So what could have caused this profound cosmic favoritism? The leading suspect is a subtle phenomenon known as CP violation. CP stands for charge and parity. In simple terms, it means that the laws of physics should treat particles and their antimatter opposites exactly the same, just viewed in a mirror. A particle spinning one way should behave identically to its antiparticle spinning the opposite way. For most of the 20th century, physicists believed this symmetry was perfect and unbreakable. But in 1964, an experiment with particles called kaons revealed a shocking truth. Very occasionally, the antimatter version of a particle decays at a slightly different rate than its matter counterpart. This tiny crack in the foundation of physics, this CP violation, showed that the universe at its most fundamental level has a tiny, built-in arrow, a preference for matter over antimatter. It's this slight difference in behavior that theorists believe allowed for that crucial 1 in a billion imbalance to emerge as the universe cooled. But here's the catch, and the reason this remains one of the grandest unsolved puzzles in science. The amount of CP violation we have observed in all our experiments to date is far too small to account for the vast amount of matter we see in the universe today. The effect we've measured is a mere whisper, not nearly loud enough to explain the cosmic shout of existence. This tells us that our current understanding is incomplete. There must be other, much stronger sources of CP violation out there, governed by physics beyond our current standard model. The search for this new physics is driving some of the most exciting experiments in the world today, from ultra-sensitive studies of neutrinos to precise measurements of the behavior of beauty quarks at the Large Hadron Collider. We are hunting for the hidden mechanism that tipped the scales in our favor, the reason we are here at all. It is a quest that goes to the very heart of our existence, asking not just how the universe works, but why it is structured in a way that allowed for us to be here to ask the question. While quarks and electrons were beginning to feel the drag of the newly activated Higgs field, Another, far more elusive cast of characters was flooding the scene in unimaginable numbers. These were the neutrinos, and they were absolutely everywhere. For every single proton or electron that would eventually survive to form atoms, there were over 1 billion of these ghostly particles streaming through the primordial plasma. At this trillionth of a second mark, the universe was so incredibly dense that even these famously antisocial particles couldn't escape interaction. They were constantly bumping into electrons, positrons, and other particles, locked in a tight thermal equilibrium with the rest of the cosmic soup. This constant chattering exchange meant that neutrinos were not just passive bystanders, they were active participants, helping to ferry energy around and directly influencing how fast the universe could expand and cool during these critical first moments. Their influence comes from a unique combination of properties. Neutrinos are electrically neutral, which means they are immune to the powerful electromagnetic force that dominated the plasma. They only feel the weak nuclear force and gravity, and the weak force has an extremely short range. This makes them incredibly slippery. But in the ultra-dense environment of the infant universe, even this weak interaction was enough to keep them tightly coupled to the fray. They acted like a subtle cosmic pressure, their relentless motion and enormous population contributing to the overall energy density of the universe. According to Einstein's equations, energy density directly dictates the curvature of spacetime and the rate of cosmic expansion. So, by simply being there in such staggering numbers, neutrinos were helping to stoke the very expansion of the universe itself, their collective gravity subtly shaping the pace of creation. This intimate tango couldn't last forever. As the universe continued to balloon in size, the density dropped rapidly. Roughly 1 second after the Big Bang, an eternity compared to our current focus, the distance between particles became so great that neutrinos simply stopped interacting altogether. They decoupled, flying free on trajectories that have been largely undisturbed for nearly 14 billion years. This event created a permanent snapshot of the universe at that 1 second mark, a cosmic neutrino background that still permeates all of space today, a fossil relic every bit as important as the cosmic microwave background that would form much later. We have not yet directly detected this neutrino background because these primordial neutrinos have incredibly low energy, but its existence is a firm prediction of our standard model of cosmology. This is why these particles are such priceless time capsules. Unlike the photons from the cosmic microwave background, which show us the universe at 380,000 years old, neutrinos carry information from a much, much earlier time. They are messengers from the first second, and by studying their properties and theorizing about their role, cosmologists can perform a kind of forensic reconstruction of the universe's earliest conditions. For instance, the number of different types of light neutrinos affects how quickly the early universe expanded, which in turn influences how much of the primordial hydrogen and helium was forged during Big Bang nucleosynthesis. Our observations of that elemental abundance perfectly match the prediction for 3 families of neutrinos, a stunning confirmation of the standard model of particle physics drawn from the first few minutes of the universe. But the story of neutrinos may also hold the key to what lies beyond our current understanding. Our models show that these particles should have played a role in shaping the large-scale structure of the universe, their gravity helping to pull matter into the cosmic web of galaxies and clusters. The precise details of how this played out depend on the neutrinos' tiny but non-zero masses. If neutrinos had different masses or properties than we currently believe, it would change the outcome of this gravitational sculpting. By meticulously mapping the universe's structure with powerful telescopes and comparing it to simulations, scientists are effectively using the cosmos as a giant laboratory to probe the physics of neutrinos. Any discrepancy between our maps and our predictions could point towards new physics, perhaps even helping to explain the nature of the dark matter that also governs the growth of structure. These faint, almost undetectable particles born in the first instance of time are therefore not just relics of the past but active guides, helping us chart a course toward a deeper theory of everything. And while the universe was still a uniform sea of quark-gluon plasma, something almost imperceptible was beginning to stir within that perfect chaos. Those tiny quantum ripples, the microscopic wrinkles in space-time that were imprinted during the inflationary epoch, were no longer just frozen patterns. They were now starting to actively shape the future of the cosmos thanks to the relentless pull of gravity. Think of it like this. If the universe were a perfectly smooth, flat sheet of glass, nothing would ever happen. It would just remain smooth forever. But if you take that sheet and introduce the tiniest of bumps, even ones too small to see with the naked eye, and then you tilt it, something remarkable occurs. Gravity acts like that tilt. Every single one of those microscopic bumps, those regions of ever so slightly higher density, began to exert a slightly stronger gravitational pull than their surroundings. It was an incredibly weak effect at first, almost negligible in the roaring frenzy of the early universe, but it was persistent and cumulative. Matter, drawn by this faint gravitational whisper, began a slow migration from the less dense areas toward the more dense ones. This process, known as gravitational instability, is what took the faint blueprint from inflation and began to build upon it, turning a theoretical map into a physical reality. This was the very first step in a construction project of cosmic proportions, one that would take hundreds of millions of years to complete. The overdensities acted as gravitational anchors. A region with just a fraction of a percent more matter would pull in a little bit more from its vicinity. This made it even denser, which increased its gravitational pull, allowing it to attract even more matter in a powerful feedback loop that scientists call gravitational collapse. It's a snowball effect on a universal scale. Yet, at this specific moment, a trillionth of a second in, this process was fighting an uphill battle. The universe was still far too hot and energetic for matter to clump together effectively. The intense pressure from the radiation-filled plasma was like a constant wind pushing against the gravitational collapse, smoothing out these nascent structures almost as quickly as they tried to form. The particles were moving at near light speed, and their kinetic energy was more than enough to overcome the still feeble tug of gravity from these tiny density variations. So while the seeds were sown and the process had undeniably begun, true structure formation was a promise for the much cooler, much older universe that was still to come. The profound importance of these quantum fluctuations cannot be overstated. They represent a stunning connection between the very smallest and the very largest scales in nature. The laws of quantum mechanics, which govern the probabilistic and uncertain behavior of particles on scales a billion times smaller than an atom, directly dictated the eventual distribution of galaxies on scales of millions of light years. It means that the eventual location of a giant galaxy cluster hundreds of millions of years later was, in a very real sense, determined by a random quantum fluctuation that occurred in the first fraction of a second. This link is one of the most breathtaking ideas in all of modern cosmology. Without these initial imperfections, without that one crucial break from perfect symmetry, the force of gravity would have had nothing to work with. There would be no starting points, no seeds, no variations to amplify. The universe would have expanded into a vast, thin, and perfectly uniform haze of particles, a cosmic desert with no stars, no planets, and no possibility for life. The fact that we exist in a structured, lumpy universe is direct evidence that its initial conditions were not perfectly smooth. our very existence is proof of a primordial randomness, a quantum roll of the dice that happened before the first tick of the cosmic clock. To truly grasp the conditions of the universe at this pivotal moment, we need to wrap our minds around the staggering numbers involved. The temperature was an almost inconceivable 10 quadrillion Kelvin. That's a 1 followed by 15 zeros. At such extremes, the conventional states of matter we know, solid, liquid, gas, are completely irrelevant. This was a realm of pure energy, where particles were moving with such ferocious energy that they were smashing into each other at velocities approaching the speed of light. The energy level for each individual particle was around 100 giga-electronvolts. While that might sound like complex jargon, it represents a very specific and crucial threshold in physics. It's the energy scale at which the electroweak force breaks its symmetry, the energy at which the Higgs mechanism kicks into gear to give particles mass, and it is the energy that defines the universe at 1/trillionth of a second. The most astonishing part of this story is that these mind-boggling conditions are not forever locked in the distant past. We can and do recreate them right here on Earth. This is the revolutionary power of modern particle accelerators, most famously the Large Hadron Collider at CERN, nestled in a circular tunnel deep beneath the border of France and Switzerland. This 27-kilometer ring is a time machine. By accelerating protons to over 99.9999% the speed of light and smashing them together head-on, scientists can concentrate an immense amount of energy into a vanishingly small point, briefly creating temperatures trillions of times hotter than the core of our sun. In the heart of those microscopic collisions, for a fraction of a nanosecond, a tiny droplet of the primordial universe flickers back into existence. We are not just theorizing about the Big Bang, we are running experiments on it. Inside these incredible machines, we don't see entire galaxies being born, of course. The scale is infinitesimal, but we see the fundamental physics that govern that early cosmos. Most notably, we can create and study the Quark-Gluon Plasma. By colliding heavy ions like lead instead of protons, we can cram enough energy into a small enough space to actually melt the boundaries of protons and neutrons, freeing their constituent quarks and gluons to flow freely for the briefest instant, just as they did in the infant universe. The data from these collisions has revealed that this plasma is not a gas, as some initially thought, but behaves as a nearly perfect liquid with astonishingly low viscosity, flowing with almost no internal friction. This discovery was a huge surprise and has profoundly shaped our understanding of how the strong force operates under extreme density. Furthermore, it was at these same energy scales that the Higgs boson was discovered in 2012. Finding this particle was the ultimate confirmation of the Brout-Englert Higgs mechanism, the process that gives other particles their mass. By producing Higgs bosons in these high-energy collisions, we are effectively witnessing the same physical process that endowed the universe with substance all those billions of years ago. Every time the LHC powers up for a new run, it is doing experimental archaeology on the first moments of creation. It allows us to test the predictions of our theories with rigorous, repeatable experiments, turning cosmology from a science of observation into a science of verification. We are bridging an unimaginable gap, connecting the largest scales of the cosmos with the smallest scales of the quantum world, all from a laboratory on Earth. But this incredible uniformity across the sky presents a profound mystery for cosmologists, one known as the horizon problem. If you look at the cosmic microwave background radiation, the ancient light from when the universe was just 380,000 years old, you find that it has almost exactly the same temperature in every direction you point your telescope. The variations are minuscule, mere fractions of a degree. This might not seem strange at first, but when you consider the physics of how information travels, it becomes a baffling puzzle. According to Einstein's theory of relativity, nothing can travel faster than the speed of light, not even the influence needed to smooth out temperature differences. This sets a strict limit on how far any signal could have traveled since the beginning of time, a boundary called the particle horizon. Now, let's calculate that for the universe at 380,000 years. Two regions of the sky on opposite sides of the universe would have been separated by a distance far greater than light could have possibly crossed in that amount of time. They were simply too far apart to have ever been in causal contact. They were outside of each other's horizons. It would be like two people standing in different cities, never having met or communicated, yet both deciding to wear the exact same outfit down to the smallest detail. Without some way to coordinate, this level of agreement is inexplicable. So how did these vastly separated regions of the early universe manage to agree on a common temperature with such incredible precision if they never had a chance to exchange information and balance themselves out? This is the essence of the horizon problem, a deep flaw in the classical Big Bang model that suggested our cosmic narrative was missing a crucial chapter. The elegant and most widely accepted solution to this puzzle is the theory of cosmic inflation. This theory proposes that an incredibly brief period of hyper-accelerated expansion occurred even before our focal point of 1/trillionth of a second. For a sliver of time around 10 to the negative 36 seconds, the universe is thought to have expanded by a factor of at least 10 to the 26, doubling in size perhaps 100 times or more in the blink of an eye. This wasn't expansion within space, it was the rapid stretching of spacetime itself. Before inflation began, the entire observable universe was smaller than a single subatomic particle, a tiny region that was small enough to be thoroughly mixed and smoothed to a perfectly uniform temperature through normal physical processes. Everything was in causal contact. Then, inflation acted like a cosmic magnifying glass, taking this tiny, homogeneous patch and stretching it to a size larger than our entire observable universe today. The vast reaches of space we see were once intimately connected, which is why they share the same properties. By the time we reach 1/trillionth of a second, the violent drama of inflation is long over, but its profound consequences are permanently etched into the fabric of the cosmos. The horizon problem has been solved. The reason the universe looks the same in all directions is because those distant regions were once neighbors, close enough to shake hands before being dramatically pulled apart. This doesn't just solve a theoretical problem, it makes a specific and testable prediction. The same quantum fluctuations that were present in that tiny pre-inflationary patch would have been stretched to macroscopic scales, creating the specific pattern of tiny temperature variations we now observe in the cosmic microwave background. The exquisite maps of this background radiation from satellites like Planck match the predictions of inflationary theory with stunning accuracy, providing powerful observational support for this incredible idea. The horizon problem, once a major crisis in cosmology, now stands as one of the strongest pieces of evidence for a much grander and more dynamic beginning to our universe. Even as the visible universe seethed with a brilliant, opaque plasma of quarks and gluons, a far more mysterious and dominant component was quietly taking shape in the shadows. This is the story of dark matter, the invisible scaffolding of our cosmos, and its origins are deeply entwined with this explosive trillionth of a second. While its exact identity remains one of the greatest unsolved puzzles in physics, we are certain of one thing: its gravitational influence began to mold the fate of the universe from these very earliest moments. The leading theoretical candidates for what dark matter actually is, whether WIMP, actions, or something even more exotic, all point to it forming or decoupling from the hot plasma right around this critical era, making its emergence a central part of the narrative. The key to dark matter's profound early influence lies in what it doesn't do. Unlike the quarks, electrons, and photons that made up the blindingly bright primordial soup, dark matter does not interact with the electromagnetic force. It is completely invisible. Light simply passes right through it. It also ignores the strong nuclear force that was desperately trying to bind quarks together. For the most part, it only feels gravity and perhaps the weak nuclear force. This aloofness granted dark matter a huge head start in the cosmic construction race. While ordinary matter was trapped in a constant, violent tug of war with radiation, the intense light pressure preventing it from clumping together, dark matter was free from all that drama. It was already beginning to respond to the gentle gravitational whispers of those primordial density fluctuations, silently pooling into the subtle over dense regions that inflation had provided. This process allowed dark matter to form the universe's first structures, vast and invisible gravitational wells long before any stars could ever shine. Think of it as an unseen framework, a cosmic skeleton. The ordinary matter, the stuff that makes up everything we can see, was like a fine mist swirling around this invisible architecture. It was only much later, hundreds of millions of years after the Big Bang, when the universe had expanded and cooled enough for atoms to form and radiation to fade, that this ordinary matter could finally succumb to gravity's pull. But it didn't have to start from scratch. It simply flowed into the deep gravitational basins that the dark matter had already patiently carved out. Every galaxy, every cluster of galaxies we see today is ultimately sitting within a massive, invisible halo of this mysterious substance. We would not have the rich tapestry of the cosmic web without this unseen foundation laid down in the first instance of time. The fact that we can be so confident dark matter existed at this early stage, despite never having directly detected it, comes from its undeniable gravitational signature on later cosmic evolution. The precise patterns of temperature variations in the cosmic microwave background are a fossilized snapshot of the universe at 380,000 years old, and they tell a very specific story. The sizes of those hot and cold spots reveal how much gravity was pulling on the plasma, and the amount of gravity required to create those patterns far exceeds what could be produced by ordinary matter alone. A significant amount of unseen, non-interacting matter had to already be there, shaping events from behind the scenes. Furthermore, the way galaxies spin and how they move within clusters provides modern-day evidence that they are embedded within these massive, invisible halos. The origins of this dominant yet elusive component of our universe are not found in the age of galaxies, but in the searing heat of its first incomprehensible moments. Yet even as quarks and gluons flowed freely in their primordial plasma, the first whispers of permanence were beginning to stir within the chaos. The universe was expanding and cooling at a breathtaking rate, and with every passing microsecond, the energy that had once kept quarks liberated was slowly fading. As the temperature plummeted below 10 trillion Kelvin, a profound shift began occurring. The overwhelming heat that had overpowered the strong nuclear force was finally losing its dominance, allowing that mighty force to begin exerting its will over the frenzied particles. This was the dawn of the Quark Epoch, a pivotal chapter where the fundamental building blocks of visible matter started to come together. In this seething cauldron, the first composite particles flickered into existence like ephemeral sparks in a cosmic forge. These were hadron's particles made up of multiple quarks bound together by the powerful exchange of gluons. The most famous hadrons, protons and neutrons, are each made of 3 quarks, but in these early moments, simpler, often short-lived combinations appeared first. Mesons, pairs of a quark and an antiquark, would spontaneously form from the immense energy of the plasma, only to be almost instantly torn apart again by a violent collision or the sheer thermal energy still present. It was a chaotic, statistical battle. For every bound state that managed to form, countless others were immediately shattered. The universe was a turbulent sea where the very concept of a stable particle was a fleeting dream, a temporary victory against the relentless chaos. This fragile process of hadronization was governed by the strange rules of the strong force, a phenomenon known as asymptotic freedom. In a beautiful paradox, the strong force actually becomes weaker when quarks are extremely close together, which is why they can behave almost independently inside the Quark-Gluon Plasma. But as the universe expands and the quarks are pulled farther apart, the force between them grows stronger, much like a stretchy rubber band. Once the energy of the surrounding plasma dropped below a certain threshold, that rubber band effect became dominant. Quarks that ventured too far from their neighbors found themselves irresistibly pulled back, snapped into bound states. This transition marked the beginning of the end for the free-flowing quark era and the start of a new age where matter could form more complex, stable structures. The formation of these first hadrons was arguably one of the most critical turning points in cosmic history. It represented the moment when the raw, undifferentiated energy of the Big Bang began to condense into the stable, massive particles that would become the bedrock of our physical reality. Without protons and neutrons, there could be no atomic nuclei. Without atomic nuclei, there could be no atoms. And without atoms, the universe would be forever barren, a thin, expanding cloud of radiation and fundamental particles, devoid of chemistry, planets, stars, or life. This delicate transition from free quarks to composite particles was the essential first step in a chain of events that allowed for the incredible complexity we see today. It set the stage for the next great cosmic milestone, Big Bang nucleosynthesis, where these newly formed protons and neutrons would fuse to create the first light elements, seeding the universe with the hydrogen and helium that would fuel the first stars. Long after the brilliant fireball of the early universe had faded, a final, crucial echo would be left behind, a whisper from a time when everything was aglow. We know this echo today as the cosmic microwave background, the CMB, a faint blanket of radiation that fills every corner of the sky. But while this ancient light wouldn't be set free until the universe was 380,000 years old, its entire story, its very blueprint, was being written right now in the frantic chaos of the first trillionth of a second. The seeds for this most important cosmic fossil were not planted during recombination, when atoms finally formed and photons began their long journey across the cosmos. They were sown in the unimaginable heat and density of this primordial era, sculpted by the forces of inflation and gravity into the subtle patterns that would one day be frozen into the sky. These seeds were the tiny density fluctuations, the microscopic ripples in the fabric of spacetime that inflation had stretched from quantum jitters to cosmic proportions. By the time our story reaches 1/trillionth of a second, these ripples are no longer theoretical. They are physical imperfections frozen into the seething Quark-Gluon Plasma. Imagine a vast, utterly smooth lake suddenly touched by a gentle, persistent breeze. The surface doesn't break into waves immediately, but tiny, almost imperceptible ripples form, a pattern of high and low pressure waiting to express itself. In our cosmic lake, gravity is that breeze. Every single region of slightly higher density exerts a minutely stronger gravitational pull. This creates a fascinating tug of war. The gravitational pull wants to collapse the overdense region to pull more matter into it. but it's fighting against the intense outward pressure of the radiation-filled plasma, which is still far too powerful to allow any real clumping to occur. So instead of collapsing, these regions become sites of subtle gravitational potential, deep but invisible wells waiting for their moment. This dynamic interplay imprints a specific signature onto the plasma. In an overdense region where gravity is stronger, a photon trying to climb out of this gravitational well loses a tiny amount of energy, making it slightly cooler. Conversely, a photon in an underdense region doesn't have to work as hard to escape, so it retains more energy, making it slightly warmer. These minute temperature differences, these anisotropies, are incredibly faint, variations of just 1 part in 100,000. But they are absolutely critical. They represent the first physical manifestation of the universe's future structure, a direct map of the gravitational landscape that was laid down by inflation and is now being subtly emphasized by gravity's relentless pull. For the next 380,000 years, this pattern will be held in a state of suspended animation, trapped within the opaque plasma. The photons are constantly scattering off free electrons, unable to travel any meaningful distance. They are prisoners within the hot soup, carrying the imprint of these gravitational hills and valleys with them. It is only when the universe finally cools enough for electrons to combine with protons and form neutral atoms, an event called recombination, that the prison gates suddenly fly open. The photons are set free, streaming across the universe, their energy and their encoded temperature patterns preserved forever. The light that was once trapped in the plasma becomes the cosmic microwave background we detect today, and the temperature variations we see in it are a direct baby picture of the universe's gravitational potential at the moment it became transparent. This is why this era is so indispensable for interpreting the CMB. The patterns we observe with satellites like Planck are not random. They are a precise record of the density fluctuations that existed in the primordial universe. By meticulously measuring the sizes and distribution of these hot and cold spots, cosmologists can perform a kind of cosmic forensics. The statistics of these anisotropies tell us, with incredible precision, the total composition of the universe, how much is ordinary matter, how much is dark matter, and how much is dark energy. They reveal the geometry of the universe, telling us that it is flat to an astonishing degree of accuracy. They even allow us to measure the rate of the universe's expansion and test the detailed predictions of inflationary theory. Every subtle wiggle in the temperature spectrum is a clue, a piece of a puzzle that leads us back to understanding the physics of the first moment, connecting the largest observable structures in the cosmos directly back to the quantum fluctuations born in the first fraction of a second. The CMB is our ultimate time capsule, and its contents were sealed and stamped during this violent, formative age. And so the great cosmic unification, that fleeting moment of perfect symmetry, came to an end. By the time the universe reached its first trillionth of a second, the era when the strong nuclear force, the weak nuclear force, and electromagnetism operated as a single, unified interaction was already a memory. The forces that would go on to govern everything from the binding of atomic nuclei to the transmission of light had found their separate identities, each with its own unique strength, range, and role to play in the evolving cosmos. This fragmentation wasn't a sign of decay, but rather the necessary next step in the universe's journey toward complexity. It was the moment the fundamental tools of creation were sharpened and specialized, each one perfectly suited for the specific tasks that would build the world we know. Yet amidst this separation, one force remained the eternal outlier: gravity. While the other three forces had danced together in unification and then gone their separate ways, gravity had always marched to the beat of its own drum. Even in those first instants, it stood apart, refusing to be neatly integrated into the grand unified scheme. This isn't to say gravity was weaker or less important. In fact, on the largest scales, it would become the dominant architect of the cosmos, sculpting galaxies and governing the expansion of the universe itself. But at the quantum level, at these unimaginably small scales, our current understanding of gravity, described by Einstein's general relativity, simply doesn't play by the same rules as the other forces, which are perfectly explained by quantum field theory. This fundamental disconnect represents the single greatest unsolved problem in theoretical physics today, the quest for a theory of quantum gravity that can finally bring this lone rebel force into the fold and complete our picture of the universe's fundamental workings. The consequences of this great separation cannot be overstated. Each force emerged from this cosmic divorce with its own unique personality and portfolio of responsibilities. The strong nuclear force, immensely powerful but with an extremely short range, became the ultimate glue, binding quarks together into protons and neutrons, and then holding those nuclei together against the tremendous electrical repulsion of positively charged protons. Without its fierce grip, atomic nuclei could never form, and the universe would lack the building blocks for all complex matter. The weak nuclear force, though less powerful, became the master of transformation, governing certain types of radioactive decay and enabling the nuclear reactions that power the stars, including the fusion processes that create the heavier elements essential for life. Electromagnetism, with its infinite range, took charge of chemistry itself, governing how atoms bond to form molecules, how light interacts with matter, and creating the vast spectrum of phenomena from electricity to magnetism to the very structure of atoms themselves. This diversification of forces created a universe of incredible richness and possibility. A perfectly unified force might have been elegantly simple, but it would have also been monotonously uniform, incapable of generating the stunning diversity we see around us. It's the specific strengths and properties of these now separate forces that make our reality possible. The precise value of the strong forces coupling constant determines how readily atomic nuclei can form. The specific nature of the weak force dictates how stars burn their fuel and how long they shine. The fine structure constant of electromagnetism controls the stability of atoms and the specific ways they can combine. Even the slightest variation in any of these values would have resulted in a sterile, lifeless cosmos. The fragmentation of the forces didn't create chaos. It created a precisely tuned toolkit that allowed the universe to build itself up from fundamental particles to complex structures, from quarks to galaxies to conscious beings contemplating their own origins. The destiny of everything was written in that first trillionth of a second, when the forces of nature chose their separate paths. To truly grasp the nature of the cosmos at this unbelievable moment, we must confront one of the most profound and persistent challenges in all of modern physics, the great divide between the two monumental pillars of our understanding. On one hand, we have Einstein's general theory of relativity, which provides a breathtakingly beautiful description of gravity as the curvature of spacetime itself. It tells us that planets, stars, and galaxies warp the fabric of the universe, and that this warping guides the motion of everything within it. This theory works flawlessly on the grandest scales, predicting the orbits of planets, the bending of light around massive galaxies, and even the existence of black holes. On the other hand, we have quantum mechanics, the wildly successful rules that govern the subatomic world. This is a realm of probability, uncertainty, and fundamental particles that can be in two places at once, a world that operates in a way that seems completely alien to our everyday experience. For nearly a century, these two theories have existed in an uneasy truce, each reigning supreme in its own domain but becoming utterly incompatible when forced to meet. And meet they must, because the universe at 1/trillionth of a second was a place where both of these worlds collided in a spectacular and violent embrace. The energy density was so unimaginably high that the sheer mass of the entire observable universe, compressed into a volume smaller than a proton, would have created space-time curvature of an extreme we can scarcely calculate. According to general relativity, this would have resulted in a gravitational field of infinite strength, a singularity. But infinities in physics are almost always a sign that our theory has broken down, that we've reached the limits of its applicability. At these scales, the smooth, geometric picture of spacetime painted by Einstein must give way to the fuzzy, probabilistic, and granular world of quantum mechanics. Spacetime itself likely ceased to be the smooth continuum we imagine, and instead became a seething, bubbling foam, a chaotic quantum landscape where the very concepts of here and now lose all meaning. This hypothetical quantum foam is one of the most mind-bending concepts to emerge from this quest for unification. Theorists propose that at the Planck scale, the fabric of reality is not smooth and continuous, but is instead a turbulent, probabilistic froth. In this foam, tiny wormholes could spontaneously blink in and out of existence, connecting distant points in space and time for the briefest of instants. Virtual black holes, pairs of particles and antiparticles that borrow energy from the vacuum to fleetingly exist, might have swarmed through this primordial chaos. It's a picture of reality that is dynamic, chaotic, and fundamentally unpredictable, a far cry from the orderly, deterministic universe of classical physics. This isn't wild speculation. It's a necessary consequence of trying to apply the uncertainty principle of quantum mechanics to the gravitational field itself. If energy and time are uncertain, then so too is the curvature of space-time they produce. This is the heart of the problem that has consumed physicists for generations: how to develop a theory of quantum gravity. We need a framework that can describe how gravity works when space-time is curled up into a tiny, hot knot, where the quantum fluctuations of gravity itself become the dominant feature. Candidates like string theory and loop quantum gravity offer different paths forward. String theory proposes that the fundamental constituents of reality are not point-like particles but incredibly tiny, vibrating strings, and that this vibration gives rise to all forces, including gravity, in a unified way. Loop quantum gravity, on the other hand, suggests that spacetime itself has a discrete, atomic structure at the smallest possible scale, woven from tiny, interconnected loops. Both are incredibly complex and mathematically daunting, and crucially, neither has yet produced a definitive, testable prediction that would confirm its validity. The drive to solve this puzzle is not merely an academic exercise. It is essential for answering the most fundamental questions about our existence. What happened at the literal beginning of time, at the singularity of the Big Bang? What is the true nature of a black hole's core? Without a theory of quantum gravity, these questions remain shrouded in mystery, places where our mathematics simply fails us and returns nonsensical infinities. The conditions of the early universe provide the ultimate laboratory for testing these ideas, a natural particle accelerator of such immense energy that it forever remains beyond our ability to fully recreate. By studying the aftermath of that era, the patterns in the cosmic microwave background, the large-scale structure of the universe, we are effectively collecting forensic evidence from a crime scene that was staged over 13 billion years ago, looking for clues that might point us toward the correct theory. This pursuit represents the very frontier of human knowledge, a testament to our insatiable curiosity to understand not just how the universe behaves, but why it is structured in such a way that it could eventually give rise to creatures like us, capable of asking these profound questions in the first place. But how can we possibly know what happened so long ago, in a realm so alien and extreme that it defies our everyday intuition? The answer lies not only in our telescopes, peering back across the vastness of space and time, but also in our most powerful machines here on Earth, massive particle accelerators that act as time machines, allowing us to recreate, in a controlled laboratory setting, the very conditions of that primordial inferno. The most famous of these is the Large Hadron Collider at CERN, a 27-kilometer ring buried deep beneath the border of France and Switzerland. Inside its circular tunnel, scientists accelerate protons to within a hair's breadth of the speed of light, and then smash them together head-on with absolutely unimaginable force. In the heart of these microscopic collisions, for a fleeting fraction of a nanosecond, the energy density becomes so incredibly concentrated that it effectively turns back the cosmic clock. Temperatures soar to over 5 trillion degrees Celsius, a heat not seen since the first microseconds of the universe, and for that brief instant, a tiny droplet of the Quark-Gluon Plasma. The very state of matter that filled the cosmos at 1/trillionth of a second flickers back into existence. By meticulously studying the aftermath of these collisions, physicists are doing something truly revolutionary. They are performing experimental archaeology on the birth of the universe itself. They are not just theorizing about the early cosmos, they are testing its physics in a repeatable, observable way. One of the most profound discoveries from these experiments was that this Quark-Gluon Plasma does not behave like a gas, as some early models had predicted. Instead, it flows as a nearly perfect liquid with astonishingly low viscosity, meaning it offers almost no internal resistance to movement. This discovery was a huge surprise and forced a major revision in our understanding of how the strong force operates under such extreme density. It tells us that the infant universe was not a chaotic, disorganized gas of free particles, but a remarkably coherent, liquid-like substance whose properties we are only just beginning to understand. Every time the LHC powers up for a new run, it provides another glimpse into this exotic state of matter, allowing us to refine our models of how quarks and gluons transition from this free-flowing plasma into the confined protons and neutrons that make up our world today. Perhaps the most famous triumph of this experimental approach was the historic discovery of the Higgs boson in 2012. This elusive particle is the visible manifestation of the Higgs field, the very entity that gives other particles their mass through the process of electroweak symmetry breaking. By producing Higgs bosons in these high-energy collisions, scientists are effectively recreating the same physical process that endowed the universe with substance all those billions of years ago. We are witnessing in real time the mechanism that broke the perfect symmetry of the early forces and allowed particles to slow down enough to form atoms, planets, and people. The detection of the Higgs was the crowning achievement of decades of theoretical work and technological ingenuity, providing direct, empirical confirmation for a cornerstone of our standard model of particle physics. It showed us that the fields and mechanisms we theorize about are not just mathematical abstractions. They are real, physical components of our universe that we can interact with and study. This transformation of cosmology from a purely observational science into an experimental one is nothing short of a paradigm shift. For most of human history, understanding the origins of the cosmos was a matter of looking outward and backward, piecing together clues from starlight and ancient radiation. Now we can also look inward into the heart of our own machines to test the fundamental laws that govern the universe's birth. The data from particle accelerators provides a crucial benchmark against which we can validate our cosmic models. If our theories about the early universe are correct, then the behavior of matter in our colliders should match the predictions. Any discrepancy becomes a thrilling clue, a potential signpost pointing toward new physics beyond our current understanding, perhaps toward the nature of dark matter or the reasons for the matter-antimatter asymmetry. These colossal machines are therefore not just recreating the past, they are actively shaping the future of fundamental physics, providing the hard evidence needed to bridge the gap between the largest scales of the cosmos and the smallest scales of the quantum world, all from a controlled environment on Earth. While the universe was no longer tearing itself apart at the exponential speed of inflation, its expansion at this juncture was still a breathtaking, violent rush. The scale factor, a measure of the universe's size relative to its starting point, was increasing at a ferocious pace, doubling in size again and again over minuscule fractions of a second. This relentless stretching was the primary driver of everything that happened next, acting as the universe's most effective and powerful cooling mechanism. Imagine a cosmic pressure cooker that is not only turning down the heat but also rapidly increasing its own volume. As space-time itself expanded, it stretched the wavelengths of all the photons and particles zipping around within it. Since the energy of a particle is directly tied to its wavelength, this stretching caused a universal and dramatic drop in temperature and energy. The incredible heat that had once kept all forces unified and particles free was now rapidly dissipating, allowing the fundamental laws of nature to settle into the distinct forms we recognize today. This cooling was not a smooth, gentle decline. It was a series of dramatic cosmic phase transitions, akin to water freezing into ice or steam condensing into droplets. The most critical of these was the electroweak phase transition we discussed, where the single electroweak force split into the electromagnetic and weak nuclear forces. This shift was only possible because the expanding universe had cooled below a specific critical temperature, around 159 giga-electronvolts. If the expansion had been even slightly slower, the universe would have remained hotter for longer, potentially delaying this transition and altering the entire subsequent chain of events. Conversely, a faster expansion might have cooled things so rapidly that certain processes couldn't complete. The precise rate of this expansion was therefore a master dial, fine-tuning the timing of these universe-altering events and ensuring they occurred in the correct sequence to build a cosmos capable of complexity. We can quantify this ancient expansion rate using a concept called the Hubble parameter, which describes how fast the universe is expanding at any given moment. Today, we measure the Hubble constant, the current value of this parameter, to be about 70 kilometers per second per megaparsec. This means for every megaparsec of distance, a staggering 3.26 million light-years, a galaxy appears to be moving away from us at 70 kilometers per second due to the expansion of space. Now rewind to 1/trillionth of a second after the Big Bang. The Hubble parameter wasn't a modest constant, it was an almost unimaginably enormous number. The universe was expanding at a rate that is utterly inconceivable on human scales, with the fabric of reality stretching at a pace that ensured its own rapid evolution from a hot, dense state to a cooler, more structured one. This frantic early expansion rate directly dictated the social lives of particles. It determined how often particles could interact before they were carried too far apart by the stretching of space. Think of it like trying to have a conversation in a crowd that is rapidly dispersing. If everyone is moving away from each other too quickly, you can't finish a sentence before you lose contact. In the early universe, this concept is known as decoupling. Particles remain in thermal equilibrium, effectively in constant conversation, as long as their interaction rate is faster than the Hubble expansion rate. But as the expansion relentlessly dilutes the density, the interaction rate eventually drops below the expansion rate, and particles suddenly find themselves out of touch, freezing out from the thermal bath and going their separate ways. This is precisely what happened to neutrinos around 1 second after the Big Bang, and it's what would later happen to photons during recombination. The timing of every single decoupling event in cosmic history was set by the precise balance between the interaction rate of particles and the Hubble expansion rate at that specific moment. This profound link between the ancient past and the observable present is what allows modern cosmologists to use today's universe as a window into its own infancy. By using powerful telescopes like Hubble and JWST to make exquisitely precise measurements of the current expansion rate, the Hubble constant, and the universe's large-scale structure, we are effectively collecting the final pieces of a cosmic puzzle. We can then run the equations of general relativity backwards in time, factoring in our knowledge of the universe's contents, ordinary matter, and dark energy. This process allows us to retrocalculate the conditions of the early universe with remarkable confidence, determining what the expansion rate must have been at 1 trillionth of a second to produce the cosmos we see around us today. It's a stunning feat of forensic cosmology, connecting the precise measurement of distant galaxies receding from us now to the violent, rapid expansion that cooled the primordial plasma and set the stage for the birth of everything. This concept of a universe cooling and expanding at a precise, calculable rate brings us to one of the most profound and counterintuitive ideas in all of cosmology: the birth of entropy and the origin of time's arrow. When we picture the infant universe as an unimaginably hot, dense fireball, our natural assumption might be that it was a state of ultimate chaos and disorder. But in the precise language of physics, the exact opposite is true. That early cosmos was actually a state of incredibly low entropy, meaning it was highly ordered and uniform. This seemingly simple observation holds the key to one of the deepest mysteries: why time only moves forward and why we remember the past but not the future. This low entropy starting point is the unsung hero of cosmic evolution, the reason why stars shine, life evolves, and history unfolds in a single, irreversible direction. To grasp this, we need to understand what entropy really represents. It's not merely chaos or messiness. It's a measure of the number of ways a system's microscopic components can be rearranged without changing its overall appearance. A high entropy state has many possible configurations. Think of a scattered deck of cards or the mixed cream in your coffee, while a low entropy state has very few, like a new deck sorted by suit and number or cream freshly poured on top. The astonishing revelation is that the universe began in the ultimate low entropy state. All that energy was crammed into an extraordinarily small volume, smoothed to near perfection by inflation, and governed by a single set of simple, unified physical laws. It was, in a very specific sense, the most orderly and organized the universe has ever been or ever will be. This initial order is the very reason we have an arrow of time at all. The second law of thermodynamics states that the total entropy of an isolated system like our universe can never decrease. It can only stay the same or increase. This is the only physical law that distinguishes the past from the future. Every other law of physics, from Newton's mechanics to Einstein's relativity, works perfectly well if time runs backwards. But entropy gives time a direction. It provides a cosmic before and after. We see eggs scrambling but never unscrambling, ice cubes melting in our drinks but never spontaneously reforming, and stars radiating their heat out into the cold void of space. All of these irreversible processes are possible only because they are moving the universe from its improbable, low entropy past toward its inevitable, high entropy future. At 1/trillionth of a second, this great march toward disorder was already in full swing, driven by the universe's frantic expansion. As space-time stretched and the primordial plasma cooled, the forces of nature were irrevocably splitting apart. This separation was a massive increase in entropy. Think of it like a beautifully organized toolbox where every tool has its specific place. Now, imagine shaking that toolbox violently and dumping all the tools into a large, empty room. The number of ways those tools can be scattered across the floor is astronomically higher than the number of ways they can be neatly arranged in the box. The transition from a unified superforce to 4 distinct forces was the cosmic equivalent of that shake, creating a vast new landscape of possible states for the universe's energy to occupy. Every particle collision, every scattering event within that Quark-Gluon Plasma was another step on this one-way journey, another notch on the entropic clock that has been ticking forward ever since. This explains why the cosmic past appears so ordered to us and the future seems destined for disorder. We are like a movie played in reverse, starting from the highly specific and improbable starting point of the Big Bang and evolving toward a more probable and generic state. Our memories and records are all consistent with this flow because they themselves are low entropy processes that require a prior low entropy state to exist. We can remember the past because it was more ordered, but we cannot remember the future because it is, by definition, less ordered. The ultimate fate of the universe may be a cold, dark, and uniform heat death, a state of maximum entropy where all energy is evenly distributed and no further work can be done. But this seemingly bleak end is not a tragedy. It is the direct consequence of a beginning that was so spectacularly special. It was that initial low entropy forged in the first instance of time that granted the universe the gift of a narrative, a story with a beginning, a middle, and an end, allowing for the emergence of complexity, consciousness, and the ability to look back and wonder at it all. Yet for all the stunning progress we've made in piecing together this cosmic story, our current understanding of physics hits a formidable wall when we try to push our inquiries to the very edge of that first trillionth of a second. The magnificent standard model of particle physics, which so accurately describes the quarks, leptons, and force carriers that emerged during this era, is ultimately an incomplete picture. It's like having a detailed map of a single continent while knowing an entire world remains to be explored. This remarkably successful theory provides no candidate for the dark matter that must have already been shaping the cosmos. It cannot fully account for the overwhelming dominance of matter over antimatter, and it offers no mechanism for the inflationary expansion that set the entire cosmic stage. To venture beyond this frontier and truly describe the universe in its infancy, physicists must turn to more speculative, ambitious frameworks that extend our understanding into realms we have not yet directly observed. This quest for a deeper theory has given rise to some of the most fascinating and mathematically elegant ideas in modern science, concepts like supersymmetry and string theory. Supersymmetry, often nicknamed SUSY, proposes a profound and beautiful symmetry between the two fundamental classes of particles, fermions, which are the building blocks of matter like quarks and electrons, and bosons, which are the force carriers like photons and gluons. This theory suggests that for every known particle in the Standard Model, there exists a massive, as yet undiscovered, superpartner. The electron would be paired with a selectron, the quark with a squark, and the photon with a photino. The implications of this are staggering. The lightest of these supersymmetric particles is a prime candidate to be the mysterious dark matter, a stable, massive particle that simply doesn't interact with light. Furthermore, the introduction of these new particles and their interactions could provide the additional sources of CP violation needed to explain why we have a universe made of matter rather than nothing at all. While evidence for supersymmetry has not yet been found in our largest particle colliders, its mathematical elegance and explanatory power continue to motivate the search. String theory takes this conceptual leap even further, proposing a radical reimagining of the very fabric of reality. Instead of point-like particles, the theory suggests that the fundamental constituents of the universe are unimaginably tiny, vibrating loops or strands of energy strings. Much like a single violin string can vibrate at different frequencies to produce distinct musical notes, these cosmic strings vibrate in different modes to manifest as the different kinds of particles we observe. A string vibrating one way might be an electron, while vibrating another way it becomes a photon. This elegant concept naturally incorporates gravity into the quantum framework, offering a potential path to the long-sought theory of quantum gravity. String theory also suggests the existence of extra dimensions of space beyond the three we experience, dimensions that are curled up and hidden from view at incredibly small scales. The specific way these dimensions are compactified could determine the laws of physics themselves, potentially explaining why we have the particular forces and particle masses that make our universe capable of supporting life. The drive to develop these theories is not merely an academic exercise for physicists. It is a necessary endeavor to solve the concrete mysteries the early universe has left for us. Without these extended frameworks, we are left with profound gaps in our narrative. We cannot explain what powered the inflationary expansion, what the true nature of dark matter is, or why the Higgs field has the specific value that gives particles their masses, a value that appears to be finely tuned to allow for cosmic structure and life. The energy scales of the very early universe, particularly those approaching the Planck Epoch, are so far beyond the reach of any conceivable particle accelerator on Earth that we must rely on the power of theoretical prediction and mathematical consistency to guide us. The cosmic microwave background and the large-scale structure of the universe act as our experimental data, the fossilized echoes of these first moments against which we can test our boldest ideas. This ongoing research represents humanity's collective effort to compile a complete theory of everything, a single, coherent framework that seamlessly encompasses all forces and all particles from the unimaginable density of the Planck scale to the vast, expanding cosmos we inhabit today. It is a grand and humbling pursuit, reminding us that every new observation from a telescope and every new datum from a particle collider is another piece of a puzzle that began its assembly over 13 billion years ago. The theoretical challenges we face today are not signs of failure but beacons, illuminating the path toward a deeper and more profound understanding of reality itself. While we have the cosmic microwave background giving us a stunning baby picture of the universe at 380,000 years old, there exists an even more ancient and elusive fossil radiation, one that has never been directly seen, the cosmic neutrino background. Imagine a faint, pervasive sea of nearly massless particles, streaming through you and everything around you at nearly the speed of light, a ghostly remnant from when the cosmos was a mere 1 second old. This is the universe's very first neutrino portrait, and it was taken at a time infinitely closer to our focal point of 1/trillionth of a second, offering a far more direct window into that searing, primordial chaos. At that 1 second mark, the expanding universe had finally cooled enough for these famously antisocial particles to stop interacting with the rest of the primordial plasma. They decoupled, flying free on trajectories that have been largely undisturbed for nearly 14 billion years, preserving a pristine record of the conditions at that exact moment. However, if we rewind just a fraction of a second back from that decoupling, to our focal time of 1/trillionth of a second, the story was completely different. Then, neutrinos were absolutely central to the cosmic drama. They were trapped in a constant, frenzied dance with electrons, positrons, and other particles, constantly colliding and exchanging energy. This tight coupling meant they were not passive bystanders. They were active participants, helping to ferry energy around the Quark-Gluon Plasma and directly influencing the rate at which the universe could expand and cool during these most critical first moments. Their collective behavior acted as a subtle form of cosmic pressure, their relentless motion and staggering numbers contributing to the overall energy density that governed the curvature of spacetime itself. Detecting this cosmic neutrino background directly represents one of the ultimate frontiers in experimental physics, a challenge that makes capturing the CMB look simple by comparison. The problem is their incredibly low energy. These relic neutrinos have been streaming through the universe for over 13 billion years, and the expansion of space has stretched their wavelengths and sapped their energy to a point where they are now astonishingly cold, moving at a tiny fraction of light speed. They are estimated to have an energy equivalent to a temperature of just about 1.95 degrees above absolute zero, which is actually colder than the CMB. To put this in perspective, a single one of these neutrinos would have less than a millionth of the energy of a photon of light that you can see with your own eyes. Their incredibly weak interaction with normal matter means that trillions of them pass through your body every second without a single one ever noticing you're there. Building a detector sensitive enough to catch even a handful of these ghostly particles would require an apparatus of almost unimaginable scale and sensitivity, perhaps using a vast volume of ultra-pure material, and waiting for the exceedingly rare occasion when a relic neutrino barely nudges an atomic nucleus. Yet the scientific payoff for such a monumental effort would be nothing short of revolutionary. A direct detection of the cosmic neutrino background would provide us with a perfectly clear, unaltered snapshot of the universe at the tender age of 1 second. Unlike the CMB, which shows us the universe after it had already cooled and become transparent to light, this neutrino fossil would show us the cosmos during its most explosive, opaque phase. It would allow us to peer past the surface of recombination, deep into the furnace of the Big Bang itself. By studying the precise properties and distribution of these ancient neutrinos, we could test our theories about the exact moment of their decoupling, measure the total number of neutrino species with unparalleled accuracy, and even probe for signs of physics beyond the standard model, such as whether neutrinos are their own antiparticles. This pristine data would act as a crucial cross-check for our models of the early universe, complementing the story told by the CMB and filling in the gaps of our understanding from the first trillionth of a second all the way up to the formation of the first atoms. It is the holy grail of neutrino astronomy, a direct line back to the universe's first breath, waiting to be unlocked. And so we enter a new chapter in the cosmic story, a period known as the Quark Epoch, which spans from that pivotal trillionth of a second all the way to 1/millionth of a second after the Big Bang. If the previous moment was defined by the dramatic separation of forces, this era is characterized by the raw, unbridled behavior of matter itself in its most fundamental form. The universe was now a vast, seething ocean of quarks, antiquarks, and gluons, a single, unified primordial fluid that physicists call the Quark-Gluon Plasma. This was not a place you would recognize in any way. There were no atoms, no atomic nuclei, not even the protons and neutrons that would later become their building blocks. Instead, the universe was filled with these elementary particles zipping around at near light speed, existing in a state of freedom they would never experience again. The behavior of this plasma is one of the most fascinating and counterintuitive discoveries of modern physics. We might naturally assume that a substance this hot and dense would act like a superheated gas, with particles bouncing off each other chaotically. But the data from our most powerful particle colliders has revealed something far more astonishing. This Quark-Gluon Plasma behaves instead like a perfect liquid, one with virtually no viscosity or internal friction. It flows and swirls with a strange, perfect harmony, a property that tells us the interactions between quarks and gluons in this extreme environment were incredibly strong and complex. This perfect liquid state suggests that the early universe, for all its unimaginable heat and density, possessed a hidden order and coherence, a collective behavior that is only now beginning to be understood. The dominant force governing this entire epoch was without a doubt the strong nuclear force, mediated by a constant exchange of gluons, but the way this force operated was utterly alien to our everyday experience. Due to a peculiar property known as asymptotic freedom, the strong force actually becomes weaker when quarks are extremely close together. This is why, in the incredible density and heat of the Quark-Gluon Plasma, quarks and gluons could behave almost as free particles, their interactions brief and their paths largely unconstrained. It was a brief window of liberty for these fundamental constituents, a period where they could exist independently before the universe cooled enough for the rules to change dramatically. And change they did. The entire Quark Epoch was a story of relentless expansion and cooling. As the universe ballooned in size, the energy density dropped, and the average distance between particles grew. This had a profound effect on the strong force. Remember that property of asymptotic freedom. It has a flip side. As quarks are pulled farther apart, the strong force doesn't just weaken, it grows stronger, much like a stretchy rubber band being pulled taut. This meant that as the universe expanded, the freedom enjoyed by quarks was progressively revoked. The rubber bands connecting them began to pull back with immense force. This set the stage for the defining event of the late Quark Epoch, hadronization. This is the process where free quarks became permanently confined into composite particles called hadrons. The most stable and familiar hadrons are baryons, particles made of 3 quarks. This is the family that includes the proton, made of 2 up quarks and 1 down quark, and the neutron, made of 2 down quarks and 1 up quark. But the transition wasn't instantaneous or clean. The universe was still a violent, energetic place, and the first hadrons to form were often unstable. Mesons, which are pairs of a quark and an antiquark, would flicker into existence only to be almost immediately torn apart again by a high-energy collision or the sheer thermal energy still present. It was a chaotic, statistical battle between formation and destruction. The final victory of matter over this chaos was a close-run thing and was deeply tied to the earlier matter-antimatter asymmetry. The Quark-Gluon Plasma was a symmetric soup containing almost equal amounts of quarks and antiquarks. As hadronization began, these pairs were primed to form and annihilate back into energy. But because of that critical 1 in a billion imbalance, that tiny excess of matter quarks, there weren't quite enough antiquarks to go around. When the music stopped and the final annihilations concluded, a small surplus of matter hadrons, protons and neutrons were left behind. Every single atom in our bodies, every star in every galaxy, is made from the leftover debris of that near-total annihilation, the survivors of a cosmic battle that ended in the Quark Epoch. This transformation from a plasma of free quarks to a universe filled with identifiable particles was the essential first step in building a complex cosmos. It marked the creation of the first stable, massive building blocks of matter, Without protons and neutrons, there could be no atomic nuclei. Without atomic nuclei, there could be no atoms, no chemistry, and no possibility for the rich structures that would eventually form. The Quark Epoch represents the moment the universe graduated from a featureless soup of energy and fundamental particles to a place where something could actually begin to stick together, setting the direct physical precedent for everything that was to follow. But our journey into the deepest nature of reality doesn't end with the story of our own universe. The extreme conditions of that first trillionth of a second and the profound questions they raise inevitably push our imaginations toward an even grander and more speculative possibility, that our entire cosmos might be just one small bubble in a vast, perhaps infinite multiverse. This isn't merely science fiction. It's a serious, though highly theoretical, extension of our most successful cosmological ideas, born from the struggle to explain why our universe looks the way it does. When we examine the fundamental constants of nature, the mass of the electron, the strength of gravity, the value of the Higgs field, we find a series of numbers that appear to be exquisitely, almost miraculously, fine-tuned for the existence of complex structures and life itself. Alter any one of these values by even a minuscule amount, and the consequences would be catastrophic. A slightly stronger strong nuclear force might bind all protons and neutrons into heavy, inert elements, preventing hydrogen from existing and stars from ever shining. A slightly weaker electromagnetic force would prevent atoms from forming stable bonds, rendering chemistry impossible. This precise calibration is known as the fine-tuning problem, and it begs a monumental question. Why does our universe have such seemingly perfect, life-permitting settings? One compelling answer offered by modern physics is that what we perceive as fine-tuning is actually a form of observational selection bias. This is where multiverse theories enter the stage. The most prominent of these ideas emerges directly from the theory of cosmic inflation. The concept of eternal inflation suggests that the rapid, exponential expansion that shaped our early universe isn't a one-time event that happened and stopped. Instead, it could be a never-ending process, a kind of meta-universe foam that is constantly boiling, with new pocket universes continuously bubbling into existence, each with its own distinct, randomly determined set of physical laws and constants. In this breathtaking picture, our entire observable universe, with all its hundreds of billions of galaxies, is just one single bubble in an endless, frothing sea of universes. We don't perceive these other realms because the space between our bubble and others is still undergoing hyperinflation, stretching far faster than light can travel, making them forever beyond our observational horizon. The events at 1/trillionth of a second become even more significant in this multiverse context. The phase transitions that occurred, the breaking of symmetries, the settling of the Higgs field into its specific value, might not have been predetermined or unique. They could have been the result of a random quantum process, a cosmic roll of the dice. In the language of physics, this is like a field tunneling through an energy barrier to settle into one of several possible stable states, a process known as quantum tunneling. In the multiverse scenario, this tunneling event might have played out differently in other budding universes. In some bubbles, the Higgs field might have settled into a different value, making all particles incredibly massive and causing the universe to collapse back on itself instantly. In others, the forces might not have separated at all, leaving a universe of pure, undifferentiated energy. We find ourselves in this particular universe, not because it's special or central, but simply because it's one of the rare types where the constants allowed for galaxies, stars, planets, and observers to eventually emerge. We are, in a sense, living in a winning lottery ticket, but in a cosmos where countless losing tickets were also printed. This idea connects the physics of the ultra-early universe directly to some of our most profound existential questions. It provides a potential naturalistic explanation for fine-tuning without invoking a designer or purpose. The constants are not fine-tuned for us. We are a consequence of their random but life-permitting values. While this remains a highly speculative domain beyond our current experimental reach, it is grounded in the mathematics of inflationary cosmology and quantum field theory. The drive to explore these ideas isn't about wild speculation, but about following the logical implications of our most successful scientific models to their ultimate conclusions. It represents the cutting edge of cosmological thought, where the quest to understand our own origins forces us to confront the possibility of a reality far grander and more strange than we ever imagined. A reality whose first and most important clues were forged in the fire of the first trillionth of a second. The quest to understand our cosmic origins is accelerating at a breathtaking pace, driven by a new generation of experiments so advanced they border on science fiction. We are no longer limited to just observing the aftermath of the Big Bang. We are building machines and instruments capable of probing its very first instance with unprecedented clarity. This isn't just about refining numbers on a chart. It's about embarking on a direct experimental hunt for the physical phenomena that shaped reality in that first trillionth of a second, from the quantum tremors of inflation to the elusive nature of dark matter. The next decade promises to transform our most profound cosmic questions from theoretical speculation into tangible, testable science. At the forefront of this effort are the next-generation particle colliders, monumental projects designed to push the energy frontier further than ever before. While the Large Hadron Collider has been our window into the trillionth second universe, future machines like the proposed Future Circular Collider aim to be 100 times more powerful. Imagine a new accelerator tunnel 100 kilometers long, circling beneath the European countryside, capable of smashing particles together with such force that it recreates conditions even closer to the very moment of Electroweak symmetry breaking. These collisions would produce Higgs bosons in vast numbers, allowing us to study their properties with microscopic precision. Is the Higgs truly an elementary particle, or does it have a hidden substructure? Does it interact with itself in the way our current models predict? The answers to these questions could reveal whether the Higgs field is the sole architect of mass or if there are other, even more exotic fields and particles waiting to be discovered, potentially rewriting our fundamental understanding of how the universe acquired its substance. But the hunt doesn't end with particles we can create in a lab. Some of the most exciting prospects come from looking not inward to the infinitesimal, but outward to the cosmos, using space itself as our laboratory. The upcoming Laser Interferometer Space Antenna, or LISA, is a revolutionary mission that will open an entirely new window on the early universe by detecting gravitational waves. Unlike the ground-based observatories that have detected waves from black hole mergers, LISA will consist of 3 spacecraft flying in a giant triangular formation millions of kilometers apart, using lasers to measure the infinitesimal stretching of spacetime. This incredible sensitivity will allow it to tune into the faintest ripples in the cosmic fabric, including those potentially generated during the epoch of inflation. The violent expansion of the universe in its first fraction of a second should have sent a storm of gravitational waves reverberating through spacetime, a permanent, if faint, echo of that primeval event. Detecting this primordial gravitational wave background would be like receiving a direct telegram from the birth of the cosmos, providing irrefutable proof for inflation and potentially revealing the energy scale at which it occurred, a clue that could directly point us toward a theory of quantum gravity. Simultaneously, the search for dark matter is entering a decisive phase. We know it shaped the universe from that first trillionth of a second, but we still don't know what it is. A new wave of incredibly sensitive experiments is now underway to finally catch this ghostly substance. Deep underground, in abandoned mines and beneath mountains, detectors like LZ and Xeno-NNT use vast vats of liquid xenon to wait for the once-in-a-lifetime collision between a dark matter particle and an atomic nucleus. In deep space, the Fermi Gamma Ray Space Telescope scans the skies, looking for the telltale gamma-ray flashes that could be produced if dark matter particles annihilate each other. And at the Large Hadron Collider, physicists are sifting through collision debris for evidence of missing energy that could be carried away by a newly created, invisible dark matter particle. A confirmed detection by any one of these methods would be a monumental breakthrough, instantly illuminating the dark half of our universe and finally revealing the identity of the particle that has been the universe's primary architect since its very beginning. It would tell us not just what dark matter is, but how it behaved in those first moments, how it decoupled from the primordial plasma, and why it clumped first to form the gravitational scaffolding for everything we see. These advances, from colossal colliders to space-based observatories, are all pieces of a single, grand endeavor to compile a complete and empirically verified history of the universe from its first moment to the present day. Each new data point helps us refine the cosmic timeline with ever greater precision, turning our theoretical models from rough sketches into a high-definition movie of creation. But perhaps the most profound implication of this research is how it connects the farthest past to the ultimate future. By understanding the initial conditions and the fundamental laws written in that first trillionth of a second, we gain the power to predict the universe's final fate. Will it continue expanding forever, cooling into a dark and lifeless void? Will it eventually reverse course in a big crunch? Or will dark energy tear even the fabric of atoms apart in a big rip? The answers to these existential questions are not written in the stars of tomorrow, but in the physics of the long-vanished Quark-Gluon Plasma. Our drive to understand our own origins is at its heart a quest to understand our ultimate destiny, showing how the story of the universe's beginning is inextricably linked to its end, and how our fleeting human existence is a meaningful chapter in that grand 14-billion-year narrative. Yet the story of our universe is not one of isolated, disconnected events, but a magnificent and unbroken chain of cause and effect, where the faintest whisper from the first moments echoed across billions of years to shape the cosmos we recognize today. The frantic, high-energy drama of that first trillionth of a second did not vanish without a trace. Instead, it set in motion a precise and inevitable sequence of events, writing a cosmic recipe whose ingredients would slowly cook into the stars, planets, and people we know. Every major epoch that followed, from the forging of the first elements to the clearing of the cosmic fog, was a direct consequence of the initial conditions forged in that primordial inferno. Consider the monumental event of Big Bang nucleosynthesis, which unfolded when the universe was just 3 to 20 minutes old. This was the period where the first atomic nuclei were assembled, and its entire outcome was predetermined by the events of that earlier, hotter era. The protons and neutrons that had only just managed to form from the cooling quark-gluon plasma were now stable enough to begin fusing together. But how much raw material was there to work with? This was decided by the critical matter-antimatter asymmetry established just moments before. That 1 in a billion surplus of matter meant that when the Great Annihilation finished, there was a specific, calculable amount of protons and neutrons left over to serve as the building blocks for all future elements. Had that asymmetry been even slightly smaller, more matter would have been annihilated, leaving behind insufficient protons and neutrons to form even the simplest atoms, rendering the universe forever barren. The precise ratio of protons to neutrons at this moment was also a direct result of how quickly the universe expanded and cooled during that first second, which in turn affected the weak nuclear force interactions that could convert one particle into the other. This ratio locked in the eventual abundances of the elements, resulting in a universe composed of roughly 75% hydrogen and 25% helium by mass, a prediction that matches our observations of the oldest regions of space with stunning accuracy. The first chapter of cosmic chemistry was written by the physics of the first fraction of a second. Hundreds of thousands of years later, another pivotal moment arrived: recombination. As the universe continued to expand and cool, its temperature finally dropped enough for electrons to be captured by protons and helium nuclei, forming the first stable neutral atoms. This event, which occurred around 380,000 years after the Big Bang, is what gave us the cosmic microwave background, as photons were suddenly set free to travel across the universe. But the story of recombination is also deeply tied to those first instants. The density fluctuations, those tiny quantum ripples amplified during inflation and then frozen into the primordial plasma, played an absolutely crucial role here. They created slight variations in the gravitational potential across space, which meant that the moment of recombination did not happen everywhere at exactly the same time or under exactly the same conditions. The photons that decoupled from slightly overdense regions had to climb out of a deeper gravitational well, losing a bit of energy and appearing cooler, while those from underdense regions appeared warmer. This is why the cosmic microwave background is not perfectly smooth, but is instead painted with those tiny temperature variations that we can measure today. The pattern of those variations is a direct fingerprint of the gravitational landscape that was seeded in the first trillionth of a second, a baby picture of the universe's potential future structure. And that future structure, the vast cosmic web of galaxies and galaxy clusters we observe today, is the ultimate legacy of those primordial seeds, the slightly denser regions imprinted onto the universe during inflation, provided the essential gravitational anchors around which both dark matter and ordinary matter could eventually gather. For hundreds of millions of years, dark matter, which had already begun to clump thanks to its freedom from radiation pressure, silently sculpted an invisible cosmic scaffolding. Then, once the universe became transparent after recombination, ordinary matter could finally fall into these pre-existing gravitational wells. The gas that would form the first stars and galaxies did not have to start from scratch. It simply flowed into the basins that dark matter had already carved out, basins whose locations and depths were determined by the pattern of those initial quantum fluctuations. The eventual distribution of everything, from the smallest dwarf galaxy to the largest supercluster, can be traced back to that random, microscopic jitter in the fields that filled the infant universe. The grand architecture of the cosmos is, in its entirety, a grown-up version of a blueprint drafted in the first instant of time. This profound continuity, this unbroken chain of causality from the quantum scale to the galactic, is one of the most powerful and beautiful ideas in all of science. It tells us that our universe has a coherent history, a story where each chapter flows logically and inevitably from the one before it. There are no random jumps, no inexplicable events. The hydrogen atoms that fused in the first stars, the helium that fills our balloons, the carbon that forms the backbone of our DNA, and the oxygen we breathe, all were made possible by the precise physical conditions established in the first fleeting moments. The galaxies that spin in the void and the planets that orbit their stars are all the grown-up children of quantum fluctuations born in a time before time had any real meaning. This narrative connects us directly to the birth of the cosmos, revealing that we are not merely passive observers of the universe, but an active and inseparable part of its great unfolding story. A story that began with a whisper and built to the complex symphony we see today. Contemplating the universe in its first trillionth of a second does far more than satisfy a simple curiosity about our origins. It fundamentally reshapes our understanding of what it means to be human and to participate in the grand narrative of existence. This journey to the very edge of time is a stunning testament to the power of the human mind. We are biological creatures, evolved on a tiny rock orbiting an average star, yet through the sheer force of curiosity and ingenuity, we have developed the tools to peer back across 13.8 billion years and reconstruct events of unimaginable brevity and violence. We did not witness this moment with telescopes. We deduced it through the elegant language of mathematics. We tested it in colossal machines that recreate the conditions of creation, and we confirmed it by reading the faint patterns encoded in the oldest light in the cosmos. This achievement is a profound reminder that the universe is not only stranger than we imagine, but that it is also comprehensible. The same physical laws that govern the orbit of a planet or the fall of an apple also govern the formation of the Quark-Gluon Plasma, revealing a beautiful and consistent order to reality that we are uniquely equipped to decipher. This profound understanding inevitably spills over from the scientific into the philosophical, forcing us to confront questions that have haunted humanity for millennia. What does it mean to exist in a universe that had such a violent and precise beginning? The fact that our reality is contingent upon a series of incredibly specific events, a slight asymmetry here, a precisely tuned force strength there, challenges simplistic notions of purpose and accident. It suggests that our presence here is both astronomically improbable and yet a direct, lawful consequence of the initial conditions set in that first moment. We are not merely in the universe, we are a product of it, literally made from the stardust forged in the hearts of stars that themselves could only form because of the gravitational seeds planted during inflation. This perspective dissolves the artificial boundary between the cosmos and the individual, revealing a deep and fundamental connection that is both humbling and empowering. It invites a sense of cosmic humility, recognizing our tiny place in the vast scale of space and time, while simultaneously granting a profound dignity to our quest for knowledge. This journey also forces a re-examination of the very nature of reality and causality. We traditionally think of cause and effect as a linear chain, a domino fall of events through time. But the early universe turns this intuitive idea on its head. At these extreme energies, the distinction between cause and effect becomes blurred. Quantum fluctuations, which are random and uncaused in the classical sense, became the cause for all subsequent structure. The entire cosmic web of galaxies, and by extension ourselves, can be traced back to a moment of fundamental uncertainty. This suggests that randomness and law are not opposites, but are deeply intertwined in the fabric of existence. The universe is not a preordained clockwork mechanism, but a system that blended precise physical law with inherent quantum randomness to produce the rich and complex reality we inhabit. It is a reality where chance played a necessary role in creating the conditions for necessity, a paradox that lies at the heart of our own being. Ultimately, this exploration enriches our perspective on the present and future. Understanding our cosmic origins provides a vital context for the challenges we face on our planet. It underscores the rarity and fragility of our pale blue dot, the only home we have ever known, and highlights the shared human adventure of discovery. The same collaborative, international spirit that built the Large Hadron Collider and the James Webb Space Telescope is the same spirit we need to tackle global issues here on Earth. Looking back to the beginning also forces us to look forward, to consider the ultimate fate of the universe and our place within that long-term story. It inspires a sense of responsibility, not just to our own generation, but to the future generations who will inherit the continuing narrative of this cosmos, a story that began in a flash of heat and light, and that we are now consciously and actively helping to tell through our science, our art, and our enduring curiosity about the world we call home. Despite the breathtaking progress we've made in piecing together the cosmic story, the journey is far from over. In fact, some of the most fundamental questions about our existence remain wide open, fueling fierce debates and driving the most brilliant minds in cosmology to search for answers that could rewrite our understanding of everything. We have a magnificent framework, a standard model of cosmology that describes the universe from a fraction of a second onward with remarkable accuracy. But this model itself points toward deeper layers of reality that we have not yet penetrated. It's like having a beautifully detailed map of a vast continent, yet knowing that the map is silent on why the continent exists in the first place or what lies on the distant shores beyond its edges. At the very top of this list of mysteries is the trigger for cosmic inflation. We have overwhelming evidence that this period of hyper-expansion happened. The large-scale uniformity of the universe and the specific pattern of fluctuations in the cosmic microwave background are telltale signs. But what actually caused it? What was the physics behind the inflatoned field that is theorized to have driven this incredible expansion? Our current models treat inflation as a necessary mechanism to explain what we see, but they don't yet reveal its fundamental origin. Some theorists propose that inflation is an eternal process, with our entire observable universe being just one bubble in a frothing multiverse of inflating regions. Others are exploring alternatives to inflation itself, such as bouncing cosmologies that suggest a previous contracting phase before the Big Bang. These debates are not just academic. The answer holds the key to understanding whether our universe is a unique event or one among an infinite ensemble, a question that strikes at the very heart of our place in the cosmos. Then there is the profound and embarrassing mystery of dark matter. We know it's there. We can chart its gravitational influence on galaxies and galaxy clusters with exquisite detail. We can watch how its immense gravity bends the light from distant objects, and we see its absolute necessity in the early universe to form the seeds of structure. It makes up about 85% of all the matter in the universe, and yet, after decades of searching, we have no idea what it is. The leading candidate for years has been a hypothetical particle known as a WIMP, a weakly interacting massive particle that would be a relic from the early universe. But despite building incredibly sensitive detectors deep underground to catch these elusive particles, we've found nothing. This null result has forced a vibrant and dynamic shift in the field, with researchers now seriously considering a much wider range of possibilities. Perhaps dark matter is not a particle at all in the traditional sense, but something more exotic like primordial black holes formed in the first second. Or maybe it's an ultralight particle called an action, which would behave more like a pervasive wave flowing through space than a discrete speck of matter. The continued failure to find WIMP has not stalled the science. It has opened it up, demonstrating the healthy, self-correcting nature of scientific inquiry where the data, or lack thereof, ultimately guides the way. Equally puzzling is the mystery of the Higgs field and its specific value. The discovery of the Higgs boson was a monumental triumph, confirming the mechanism that gives all other particles their mass. But this victory came with a deep and unsettling question. Why does the Higgs field have the specific strength that it does? The mass of the Higgs boson itself seems unnaturally fine-tuned. According to our best calculations, quantum fluctuations should drive its value to an astronomically higher number, a scale trillions of times larger than what we observe. This would make the Higgs field so powerful that it would give electrons and quarks immense mass, preventing atoms from ever forming. The fact that we exist in a universe where the Higgs value is just right for chemistry and life seems like a cosmic coincidence of staggering proportions. Some physicists see this as a clue pointing toward new physics, like supersymmetry, which would introduce partner particles that cancel out these extreme quantum corrections and naturally explain the Higgs's low mass. The absence of evidence for supersymmetry at the Large Hadron Collider so far has made this puzzle even more acute, pushing cosmologists to consider even more radical ideas to explain why our universe seems so curiously arranged for our existence. These are not minor gaps in an otherwise complete picture. They are yawning chasms in our understanding that point toward a reality far stranger than we have so far dared to imagine. Resolving them will require more than just bigger versions of our current experiments. It will demand revolutionary new ideas, perhaps a complete overhaul of our understanding of space, time, and particles. The next great leap might come from a radical new theory of quantum gravity, or from an unexpected astronomical observation that completely overturns our current paradigm. This is the thrilling and dynamic state of modern cosmology. It is a field that is simultaneously incredibly successful and profoundly humble, aware of how much it has uncovered but also keenly conscious of how much more lies hidden in the darkness, waiting for the next flash of human ingenuity to bring it into the light. When we try to picture the beginning of everything, we often reach for the most dramatic imagery we can find. A single point of infinite density suddenly exploding into being, a universe popping out of absolute nothingness. These popular descriptions are powerful and evocative, but they can also be deeply misleading, creating a series of persistent myths that even some documentaries and popular science articles accidentally reinforce. The classic idea of the Big Bang singularity, for instance, is often presented as a literal explosion from a specific point in space. This conjures an image of the universe unfolding into a pre-existing, empty void, like a firework bursting in the night sky. But that's not what the theory actually describes. The expansion of the universe isn't matter flying outward through space. It's space itself stretching, carrying galaxies along with it like raisins in a rising loaf of raisin bread. There was no center to that explosion because every point in the universe today was once that same point. The entire observable universe, in all its vastness, was compressed into an incredibly hot, dense state, and it's been expanding everywhere at once ever since. Another common oversimplification is the idea that the universe came from nothing. This is perhaps the most philosophically charged misconception. In everyday language, nothing implies a complete and total void, a pure absence of anything whatsoever. But when physicists talk about the universe emerging from nothing, they are often using the term in a very specific technical sense. They are referring to a quantum vacuum, a state that is seething with potential energy and governed by the bizarre rules of quantum mechanics. This nothing is not a true nothing. It's a something with well-defined properties where particles can spontaneously flicker in and out of existence. The universe likely didn't spring from a philosophical nothingness but from a pre-existing quantum state whose origins are still a complete mystery to us. This distinction is crucial because it moves the question from the unanswerable, why is there something rather than nothing, to the potentially answerable within the framework of physics. What are the laws that govern the quantum vacuum from which our universe emerged? Perhaps the most significant clarification we can make is about the very concept of a beginning. The classical Big Bang model, with its inevitable mathematical singularity where density and temperature become infinite, is a clear signal that our current theories break down. It's not a description of a physical reality, it's a signpost that says here be dragons. Most cosmologists now believe the universe did not have a literal beginning in time as we understand it. Instead, it likely emerged from a prior state, a quantum gravitational realm or a cycle of universes, where our familiar concepts of time and causality simply do not apply. Asking what happened before the Big Bang might be as meaningless as asking what is north of the North Pole. Time, as we experience it, may have begun with the expansion of our universe. This doesn't make the origin any less profound, but it frames it not as a moment of creation from nothing, but as a transition from one state of physical reality to another, a transition we are still striving to understand. Dispelling these myths is not about robbing the cosmos of its wonder. It's about replacing a simplified and sometimes incorrect story with a far more fascinating and intellectually honest one. The real narrative isn't about a magical explosion, but about a natural process governed by physical laws we are slowly deciphering. When we educate the public about these nuances, we do more than just correct facts. We foster a much deeper and more genuine enthusiasm for science. We show that the universe isn't a completed puzzle, but a dynamic, ongoing investigation, full of mystery and breathtaking complexity. It invites everyone to appreciate the real, hard-won achievements of cosmology, not as a set of final answers, but as a magnificent, evolving conversation about the nature of reality itself. This engagement builds a foundation of scientific literacy that is essential for a society that must navigate an increasingly technological world, empowering people to think critically and share in the awe of our collective quest to understand the cosmos. But how do scientists move from these grand theoretical ideas to concrete, testable predictions about the early universe? They use some of the most powerful tools in modern science, not telescopes or particle colliders, but vast supercomputers running incredibly detailed cosmic simulations. Think of these not as simple animations, but as virtual laboratories where physicists can recreate the entire history of the cosmos, from a fraction of a second after the Big Bang right up to the present day. These aren't just artistic renderings, they are complex mathematical models that incorporate all the known laws of physics, from general relativity and the behavior of dark matter to the hydrodynamics of collapsing gas clouds and the feedback from exploding stars. Researchers input their best understanding of the initial conditions, those quantum fluctuations from the inflationary epoch, and then press play, letting the unbreakable rules of physics dictate what happens next over billions of virtual years. The primary goal of these simulations is to act as a crucial testing ground for our theories. Scientists can run countless experiments in these digital universes, tweaking one parameter at a time to see how it changes the outcome. What happens if dark matter is slightly colder or warmer than we think? How does the strength of the supernova explosions that eject heavy elements into space affect the formation of the next generation of stars? By running these virtual experiments, cosmologists can generate precise predictions for what we should observe in the real universe if a particular theory is correct. They can create a simulated cosmic microwave background with a specific pattern of fluctuations, or they can predict the exact distribution and properties of galaxies and galaxy clusters that should emerge across space. They then take these predictions and compare them directly to the exquisite maps from telescopes like the Planck satellite and the Sloan Digital Sky Survey. When the simulation matches the observation, it's a powerful vote of confidence for the underlying theory. When it doesn't, that discrepancy is a gold mine, a clear sign that our understanding is missing a key piece of physics, guiding researchers toward the next breakthrough. Perhaps the most famous and ambitious of these projects is the Illustris TNG simulation, a monumental computational effort that models a cubic volume of the universe over 300 million light-years on a side, from just a few 100,000 years after the Big Bang to the present. This simulation doesn't just track dark matter, it also follows the ordinary matter that makes up stars, planets, and us. It models the complex dance of gravity pulling gas into galaxies, the violent birth and death of stars that heat and enrich the surrounding gas with heavy elements, and the powerful jets erupting from supermassive black holes at the centers of galaxies. The result is a breathtakingly detailed virtual universe that looks astonishingly like our own, complete with majestic spiral galaxies, ethereal gas filaments stretching between massive clusters, and vast, empty cosmic voids. By studying this synthetic cosmos, researchers can watch a galaxy like our own Milky Way form from start to finish, tracing its entire history in a way that is impossible with real-world observations alone. The beauty of these simulations is that they are now becoming accessible to everyone. Many research groups have created stunning visualizations and interactive portals that allow students and the public to explore these virtual universes from their own computers. You can fly through a galaxy cluster, watching dark matter halos merge and galaxies collide in a dynamic cosmic ballet. You can rewind the evolution of a single spiral galaxy, watching it grow from a tiny density fluctuation in the early universe into the grand structure we see today. These tools transform abstract concepts into tangible, visceral experiences, making the incredible story of cosmic evolution something you can not just hear about, but actually see and explore for yourself. They are powerful educational instruments, demystifying the cosmos and inspiring the next generation of scientists by showing them that the universe's greatest mysteries are not beyond our grasp, but are instead puzzles we are actively solving through a combination of brilliant theory, cutting-edge technology, and relentless human curiosity. From a seething plasma of quarks and gluons to the structured cosmos we see today, the universe at 1/trillionth of a second was a crucible of creation. Every force, particle, and asymmetry from that era shaped the stars, planets, and life itself. As we continue to probe these earliest moments, we not only unravel cosmic history, but also explore the fundamental laws of nature. Reflect on this incredible journey, share your thoughts below, and join us in marveling at the universe's grand narrative. This journey into the dawn of time reveals a cosmos of breathtaking elegance and profound interconnectedness. The same quantum fluctuations that were amplified during inflation went on to become the galaxies we observe with our most powerful telescopes. The slight asymmetry between matter and antimatter ensured that there would be something rather than nothing left to build upon. The precise strengths of the fundamental forces allowed for the formation of stable atoms, complex molecules, and eventually the possibility of life itself. We are not merely observers of this cosmic story, we are active participants, our very existence woven into the fabric of the universe from its very first moments. The quest to understand our origins is far from over. Each answer we uncover opens new and even more fascinating questions. What is the true nature of dark matter, and when did it first begin to shape the cosmos? Did inflation occur, and if so, what triggered it? Could our universe be one of many in a vast multiverse? These are the mysteries that drive the next generation of scientists, engineers, and dreamers. With more powerful particle colliders, increasingly sensitive space telescopes, and ever more sophisticated computer simulations, we are continuing to push the boundaries of what is known, forever refining our story of how everything began. This exploration does more than just satisfy our curiosity. It fundamentally changes our perspective on our place in the cosmos. Knowing that the atoms in our bodies were forged in the hearts of long-dead stars is a profound and humbling realization. Understanding that the laws of physics that govern a falling apple also govern the formation of the first particles connects us to the universe in a deeply meaningful way. It is a story of how order emerged from chaos, how complexity arose from simplicity, and how, against inconceivable odds, the universe woke up and began to understand itself through us. So the next time you look up at the night sky, remember that you are not just looking out into space, you are looking back in time. The light from those distant stars is a messenger from the past, and the physics that governs their shining is the same physics that was decided in the first trillionth of a second. It is a grand 14-billion-year-old narrative, and we are incredibly fortunate to be living in a time when we can begin to read its opening chapters. This story belongs to all of us, a shared heritage of wonder and discovery that continues to unfold with every new observation and every new